Thank you very much for the presentation. Thank you very much to the organizers for giving me the opportunity to give this talk. I want to talk about part of my PhD thesis, which I'm doing under the direction of Jordi López Abad at the UNED. So what I want to talk about is the Banach-Saks rank, and basically the Banach-Saks property and how does it work and what goes well and what goes bad. So it all started back in the 1930s or so. There's this really well-known theorem of Massou, which tells us that if you have a weakly convergent sequence, then you can always make it non-convergent by sacrificing that you have to take convex combinations, a sequence of blocks of convex combinations. So what people started questioning is, well, how complex are these convex combinations? Can I just take, for example, averages? And that's a well-studied notion, which is Chesrow convergence. A sequence is Chesrow convergence if the averages converge to the point. This is weaker than usual non-convergence because if the sequence converges, then its average converges too, but the other way around doesn't work, even in the real line. So say we have a weakly convergent sequence, can we take at least a subsequence so that the averages converge at some point? And Banach and Saks proved in 1930 that the answer is yes, at least in some spaces. So in the LP spaces within the reflexive range, every bounded sequence has a Chesrow convergent subsequence. So this is a really nice result, and we can give this property a name. So let's say that a subset of a Banach space has the Banach-Saks property if every sequence in the set has a Chesrow convergent subsequence. Just one small comment, we have to make this stuff of always passing to subsequences because Chesrow convergence doesn't pass. So you can have in R, for example, you can have a Chesrow convergence sequence and then find a subsequence which goes to infinity very fast and doesn't converge in any way. Well, we have that. We say that the space has the Banach-Saks property if its unit ball has it. So every bounded sequence has a subsequence which is Chesrow convergent. So people started to study this notion, and they said, well, the Banach-Saks property, all LP spaces have it. This is just Banach and Saks from 1930. They asked, well, what happens, for example, with the space of continuous functions over the interval 0, 1? And here there's a lot of people already, even like this morning, which have talked about the Schreier space. Schreier actually proved that the space of continuous functions over omega to the omega there's a sequence that doesn't satisfy this property. But like the question Banach and Saks asked was about C01. And since every sequence you can represent it in C01, they said, okay, the answer is no. So what goes wrong in C01? Well, of course, reflexivity, because you need to assume that the sequence is weakly convergent. If not, the other way around, if you have a sequence such that every subsequence has a further subsequence which is Chesrow convergent, then pushing this argument a bit further, you can show that it has a weakly convergent sequence. So what I just said is reflexivity. There is a more formal argument for this implication, which is really nice, which is using very strong theorem, which is Rosenthal's L1 theorem. And this will appear later. But the thing is, assume you have a sequence and assume that every subsequence you can pass to a further subsequence which is Chesrow convergent. Then you say, well, what happens with L1? Rosenthal's L1 theorem tells me that there can be a subsequence that is equivalent to the L1 basis, but this property tells me no, because whenever I take convex combinations of the L1 basis, what I get is isometrically equivalent to the L1 basis, which is never going to converge. So that cannot happen. And then Rosenthal is telling me that then there is a subsequence which is weakly Cauchy. And if it's weakly Cauchy, and if it has these convex combinations which converge somewhere, then I can actually prove that it's weakly convergent. So what I show is that the Banach-Saks property implies reflexivity. Nishiro and Waterman, what actually did in the paper was to provide a characterization of reflexivity in terms of summability methods. So a space is reflexive if and only if, for every sequence, there is some summability method that sums some subsequence. But nevertheless, this implication was true. And on the other side, we have super reflexivity, which which is being isomorphic to a uniformly convex space, if you want to see it that way. Kakutani proved that superreflexivity implies the Banach-Saks property. If your space, if the ball of your space is like sufficiently convex, then you can actually always find a subsequence which is convergent, but the converse doesn't hold. And in the same paper, he provides both examples. And so in this whole diagram, the only thing left is some backwards arrow here. So we say, okay, in a reflexive space, every bounded sequence has a weakly convergent subsequence. Maybe if I play around with things, I can make it to be tetrahedral convergent. And there's been already talked about the Bernstein space. He provided the first example of a space which doesn't satisfy. So it's a reflexive space, but there are bounded sequences without weakly convergent subsequences, so without tetrahedral convergent subsequences. So this was the diagram, and people later in the 90s tried to push this further and try to, in particular, fill the gap that stays within this property. So, okay, if it's Banach-Saks, then it's reflexive. But if it's reflexive, maybe, well, I cannot take averages once, but maybe I can expect that every sequence has a subsequence such that the averages of the averages converge. So they were trying to formalize this, and the best way to do it was like trying to redefine a bit what tetrahedral convergence is. So tetrahedral convergence is about taking averages, taking from the first element to the last one, and sort of more in the spirit of Mathuros' theorem, they wanted to turn this into a notion of block sequences of convex combinations. And this is a very easy result to prove. This is basically just a computation. If every subsequence has a further subsequence, which is tetrahedral convergent, that's the same as saying, if you give me a subsequence, I can find a sequence of blocks such that these convex combinations converge to some point. So I have a particular form for the convex combinations. However, I need to add one condition, and it's this condition here. And from the previous talk, you recall that this condition is basically saying that the support of these convex combinations have to be in the Schreier family. So Alspach and Agiros noticed this and said, well, we have a way of extending this notion of the Schreier family. So they defined the Schreier hierarchy. So this is a sequence of families of finite subsets. I'm going to make a little diagram here, because instead of thinking of families, you can think of sequences. So what are we going to do? Well, I have my sequence here, and for the first Schreier family, the one for the 0, I'm just going to take the singletons. That's just one point, which means taking convex combinations with support in S0, in convex combinations with support here, is just taking a subsequence. Now, the next part is, we've already talked about the Schreier family. So now I want to take blocks, but somehow the first element of the block tells me how many more I can take afterwards. So if, say, I start here at n, then afterwards I can take as many points as I want to form my block, but, sorry, I can take any points I want, but at most n more, and nothing else. So the farther away I am, the more long this block gets. How can we generalize this for further ordinals? Well, we can see these blocks as blocks of points, which is blocks of the previous family. So for the successor, we just say that's the formal definition, but for example, S2, what I will say is I have these blocks here on top. So I'm going to take one block, whichever I want, and after it, I'm going to take any blocks I want, but at most, whatever this number here is telling me. So I can take this block, I can take this from over here, and this whole thing would be my block in the second Schreier. So this is like a way of saying we are forming blocks of blocks, and by this process we are constructing more and more complex combinations. In the limit case, well, we just fix a sequence that is increasing to whatever ordinal we have, and then we sort of, for each n, we look at the Schreier family of the corresponding ordinal here, they defined this to prove another thing, but well, we could try to replace this in this proposition here, and like, what could go wrong? Well, some things could go wrong, because there is a thing that might make this whole Banach-Saks stuff fail completely, and that worst enemy is a 1. And the answer is what I said before. If you have the canonical basis of a 1, and you take blocks of convex combinations, what you're going to get is isometric to the canonical basis of a 1 again, so you're not expecting to get anything convergent at all. But, well, the canonical basis of a 1 is not weakly convergent, so it's a bit of cheating. If I have weakly convergent stuff, this shouldn't happen. What happens is that you don't have to have the full L1. You just have to have something that looks like it. And the correct notion, well, there's an example, which is the Schreier space, which was constructed specifically for this. It has an unconditional basis, which is weakly null, so we should expect some convex combinations going to 0. But definitely not with the Schreier family. So in any case, we would have to go to S2 or whatever. So the reason is that this basis looks like a 1 asymptotically, because if you remember what we were doing when we were computing this Schreier norm was we take one of these blocks, and along the block, we sum the absolute value of the coordinates. So along this block, we get something like L1 or L1 of the corresponding finite dimension. The problem is these blocks get larger and larger as we go further. So this starts to look more and more as the space L1. The correct notion again for this is spreading models. We say that the sequence in a Banach space is an L1 spreading model if there exists some epsilon such that basically the sequence looks like L1, but only in elements of the Schreier family, which get larger and larger. So we have things that look more and more like L1 every time. But it's not the full L1. It's not necessarily the full L1. The reason why the Schreier space fails this Chesor convergent stuff is because the canonical basis is an L1 spreading model. But now, Alsberg and Agios, they had this generalization of the Schreier families. So I can just replace here the Schreier family for the psi, and then I would have an L1 psi spreading model. And here I would say that the universal basis of the Schreier space as an L1-1 spreading model, because I want to specify the dependence on the ordinals. In this paper, they proved that these sequences that look like L1, they have to stop somewhere at some countable ordinal, or otherwise you just have the full L1. So if you have in a sequence, spreading models for every countable ordinal, then you actually have the full L1. So you have no hope for Chesor convergence. So these are sort of the bad guys of the picture, because if they look like a 1, then no hope for convex combinations to converge, or at least they have to get really complicated. We can counterpart this by making complicated convex combinations. And that was done later by Agios, Merkourakis, and Tsaparias in '98. So they took these families and they said, okay, let me put particular convex combination here, and let me evaluate these against the L1 and let them have a fight and see who wins. The definition is a bit technical, but it's what you would expect. So if you have a singleton, which convex combination are you going to take? Well, you just take one here, and that's the only thing you can do. If you have already defined zeta convex combinations, how do you go to zeta plus 1? Then, well, you have these blocks here, and you have a convex combination in each of these. So you just take your union of blocks, and then say, okay, I take all these convex combinations, and I take the average of all of them. So that's the point. And then in the limit ordinal, you just do the appropriate limiter stuff. You just look to the previous family where everything was defined, and you take the average from there. With this convex combination, I can specify what do I mean by Jezero convergence of order, whatever ordinal I want. So a sequence is psi-summable if there is a block sequence of psi-repeated averages of these, like, probably very complicated averages, such that when this pairing here is like, you take the coefficients of an and you multiply by the corresponding xn and you add them up, if this sequence converges in norm. So these are the bad guys. The L1 spreading models, sorry, these are the good guys. The L1 spreading models were the bad guys, so we can have a fight and see who wins. And for every weakly null sequence, exactly one wins. So this is actually the good notion of Jezero convergence of order psi, which is that for each weakly null sequence, and you give me an ordinal, then exactly one of these things is going to hold. Either it is an L1 spreading model, in which case I cannot sum it with convex combination of complexity psi, or I can sum it with convex combination of complexity psi, and then it's not an L1 spreading model. And exactly one of the two must happen. So perfect, we have a rank. We say you give me a separable subset, and we define its Banach-Saks rank as the minimum ordinal whenever it exists. It might not exist, such that every sequence in A has a psi-summable sequence. So for psi equals 1, this would be one summable, which is the same as Jezero convergence. So this is Banach-Saks rank 1 is exactly the Banach-Saks property. I say if it exists because they prove, they prove it for the unit ball, we prove it for arbitrary subsets, that for it to exist, the subset has to be, of course, relatively weakly compact, because you need every sequence to have a weakly convergent subsequence. Otherwise, there's no hope for any convergence of the convex combinations. So what we obtained, apart from generalizing these two arbitrary subsets, was, well, first of all, these particular convex combinations that Argyros, Mercourakis, and Saparlias got, you can actually just take any. The only important thing is the support of these convex combinations. If you look it the other way around, if you're looking at L1 spreading models, you will realize that this is actually a combinatorial problem, because you're looking at a sequence as you're looking at which subsets or which combinations of elements of the support you have some condition. This is actually another way to see that this is a combinatorial problem, because the particular coefficients you put here do not really matter. The only thing that matters is that the supports are in a family, the Schreier family of order psi. In fact, the particular Schreier family does not really matter. You can really replace it by anything that is, so this psi has a lot of properties, is compact, for example, is spreading, which basically means that if I have this block and I just move it over here, then it will still be in the family. And it is something called omega C uniform, which is something I'm not going to talk about because that would be too many definitions already. But what this says is that, well, the particular family doesn't matter. What really matters is the complexity you put here. Okay, but some other thing we would like to say is that this is fine, this is well defined, but do I have any way of knowing which convex combinations do I need to take? Because you give me a weakly convergent sequence, and I want to find a particular, what's its rank? How do I, at which level of this Schreier hierarchy do I have to stop to have weak convergence? So we want to have some bound that maybe depends on the sequence. And well, we were able to prove some, it might seem a bit technical, but just, so I have a weakly convergent sequence and I just define a certain family of subset, which is the family of all subsets where the sequence is away from its limit and in a way that I can measure, so in a weak way that I can measure with an element of the dual. And if I have this family, then by knowing the complexity of his family, and by complexity, I mean some restrictions that have to be uniform, but basically have an estimation of what the Banach-Saks rank will be. So this is a bit of a more explicit way of knowing what the Banach-Saks rank is of a given sequence or set. But the whole point of studying the Banach-Saks rank in my PhD thesis was that we wanted to answer a question. And it's a question about some well-known theorems. So Masur's theorem tells me that if a set is compact, then its convex hull is compact too. Then I have Klein-Smulian theorem that tells me that if A is weakly compact, then the convex hull is weakly compact too. But the Banach-Saks property sits in between. So, well, it should be. And like the answer is intuitively, of course, yes. Not only because it would make this diagram look nicer, but also because what we are doing is all about taking convex combinations. So if I have a set, say, here, and I know that, for example, it has the Banach-Saks property, which means that in every sequence I just have to take averages. Well, when I take its convex hull, any point in the remainder will be a convex combination of points in the original set. So this point is made by convex combination. So to make these points converge, I shouldn't have to take further averages. It should be at most like even less, but okay, the original set is in there, so it should be the same. And intuitively, it is very true. In reality, it's not. There is a work from 2013 by Lopez Abad, Reid, and Tradacete, in which they show that there exists such a set which has Banach-Saks rank, but its convex hull has Banach-Saks too. Which means that somehow the convex hull is more complicated in order to take averages that converge. So we wanted to answer a question. Well, is this the worst scenario? Like, is this the worst that could happen? Intuitively, it should. Like, this convex hull shouldn't have much higher rank than the original rank. Well, we know we have to at least one, but maybe not. The problem is we didn't know how to tackle this question at first. It seems really complicated because a direct argument doesn't seem to work. If I have a sequence, in the convex hull, say, then each point is made of points from A, etc. Then I want to refer to the Banach-Saks rank of A. So I say, okay, there are blocks of convex combinations here that converge in norm to some point. The problem is these blocks break the convex combinations I already had. So these blocks do not have to represent the same points I had before, so I cannot conclude anything about the original sequence. And there seems to be no direct argument. So we said, okay, we don't know how to answer this question. Let's just change it. Let's just say, okay, we at least cannot have something completely wild. We cannot have a set that is really simple in this sense, but whose convex hull is arbitrarily weird, with arbitrarily high rank. So maybe not +1, but maybe there is an ordinal function such that I can sort of compute or bound the Banach-Saks rank of the convex combination by the Banach-Saks rank of the original set. So what we tried was a bit of descriptive set theory. And just, I'm going to rush a bit through this part. But basically, well, every separable set can be seen as every separable set in a Banach space is every separable closed subset of a Banach space is a closed subset of C01 up to isometry. So we work with closed subsets of C01. So these are all the objects we want to take a look at. Here, there happens to be a really nice sigma algebra, which is the F-first Borel, which is generated by some sets. And the thing about it is that this pair, this family of closed sets with a sigma algebra, they are a really nice space. They are what's called a standard Borel space. And that means that there is a Polish topology on my set, which is not important for us. But there is some Polish topology there that makes it, whose Borel sigma algebra is precisely this. So it's a nice space to work with and to do descriptive set theory. We can talk about Borel sets, we can talk about analytic sets, etc. In particular, our rank is only defined for relatively weakly compact sets. So I take this family, and it happens to be co-analytic by some results of James, which characterize when a set is relatively weakly compact. So then we went looking for books in which these notions appeared, and we found that there's a whole thing in descriptive set theory called rank theory, and they have this really nice notion of co-analytic ranks. I'm not going to go into the definition of co-analytic ranks because it's like very complex and everything, but basically they have nice properties. And the main property that we wanted to take a look at is that any two ranks defined, any two good ranks, co-analytic ones, are equivalent. And this is what we want. So is it maybe co-analytic? If it was, then the answer would be yes. We would evaluate, compare this rank with this other one. So is it? And the answer is, of course, no. It is not. It's not, well, it could be equivalent and that would be enough, but it's not even bounded below by a co-analytic rank. So we have, well, I have an idea of the proof here, but it's not really important. But the thing is, we are stuck. The original counterexample of Jordi, Ruiz, and Radacete, we have not been able to generalize it to have like more complex stuff. Like maybe the answer to this question is no. We haven't been able to do that. And without this sort of powerful theory of co-analytic ranks, we really do not know how to proceed here. So I would like to end like Professor Castillo ended yesterday with a call for help. Any ideas are welcome. We don't know if the answer is yes or no. We don't know how to prove any of both things. But thank you very much for your attention. Here you have a few references, and that's all. Mm-hmm. Okay. Okay. So, yeah. Okay. Okay, I will look at that. Thank you.
Next talk is in 2 minutes. Started and I didn't know how to.
I wanted to look at it, but it was like off. I'm sorry.
Yeah, because it didn't start. At some point, I was starting to look at
Yeah. Ah, sorry. I'm sorry.
speak.
I'm sorry. Do I remove this? More complicated than it looks.
I don't know. It's not shape for years. And
You like this? Oh, the middle one. Okay.
That's how my talk is the last one, so we can.
Yeah, exactly. And also, last speaker in this morning is
Thank you, and let me also thank the organizers for this conference. It has been a very lovely time so far. So today I will like to talk about our recent joint results with Anna Pelcher-Bervac and Tomáš Rosický about the separable Banach space of a non-trivial Baire order. So let me stress that those are results in progress, so keep that in mind. Okay, so let me first introduce you to the problem. So we will consider a separable Banach space X. So the important thing is separable. I will probably sometimes forget to mention it, but in this talk, X will always be separable. And we consider it embedded in the bidual, and we call this image of this embedding by X0 double star. And what we do next is that we recursively build a hierarchy of intrinsic Baire classes of X just by taking iterated weak star sequential closures. So we begin with X, that's X0 double star. Then X1 double star would be the set of all weak star limits of sequences from X. X2 double star will be the set of all limits of sequences from X1 double star, and so on. So we naturally iterate this construction in this way. And this should explain why we call it Baire classes of X. Because we begin with something continuous, and then we take pointwise limits. So this is precisely how Baire classes are defined. Then there is also this word intrinsic that I will comment more about in the next slide. But let me first give you some examples. So on one hand, it is true that our Banach space is weakly sequentially complete if and only if X equals the first Baire class functionals. Why is this? This is because weak sequential completeness can be equivalently rephrased to the fact that if you have a sequence from X that weak star converges in the bidual, then the limit also has to be in X. So this precisely means that X is already sequentially closed in the weak star topology. Yeah, so in the case our space is weakly sequentially complete, we are not going to get some nice hierarchy of Baire classes because everything will always be the same. It will always be just the continuous function, weak star continuous function. On the other hand, if we take as our X the Banach space of continuous functions on the interval, it can be shown that then the intrinsic Baire class alpha can be identified with the space of all bounded alpha Baire functions on the interval. And it is well known that those Baire classes are strictly increasing for every countable ordinals. So for this case, we have like the full increasing chain of length omega 1 of Baire classes. And finally, by the result of Odell and Rosenthal that was mentioned in the Instro Todorčević's talk the first day, we have that X does not contain left to L1 if and only if everything in the bidual is already a Baire 1 function. So let me stress that here we use separability. This is not just a corollary, this is more or less the statement just written in this language. Okay, so now the promised comment about the word intrinsic. So it is important to distinguish between being in the intrinsic Baire class alpha and being a function that just randomly happens to be of Baire class alpha. So let me illustrate this for these examples. So for the Baire class 0 functions, it works. It is true that if you have a function in the bidual, then it's weak star continuous, if and only if its restriction to the ball is weak star continuous. So we have this equality over here. The same works for Baire 1 functionals by the result of Choquet, that the first intrinsic Baire class are precisely those functionals whose restriction to the ball happens to be a first Baire class. So one might think that this would be true for every alpha, but this is not true for every alpha. There is actually an example by Talleyrand of a Schur space, so in particular weakly sequentially complete space. So we have that all the classes are trivial, it's just X, but such that we can find a discontinuous element of the bidual whose restriction is of Baire class 2. So this element is not an element, it's not element like this, the intrinsic Baire class, but its restriction happens to be Baire function. Yeah, this is because the reason why this restriction is of second Baire class is that it can be approximated by Baire1 nonlinear function. It's the limit of Baire1 nonlinear functions. So yeah, but in order for it to be in the X2 double star, it would need to be a pointwise limit of functions that are simultaneously linear and Baire1. Yeah, so it is important to distinguish between the intrinsic classes and just the classes. Yeah, so the word intrinsic is there because those classes are built from inside from X. Like you cannot approach the property from the outside. Okay, so now when we know the definition of Baire classes, we can define a natural Baire order of a Banach space, of a separable Banach space, to be just the smallest ordinal alpha where this iteration stabilizes. So the smallest alpha such that X alpha double star is already weak star sequentially closed. This is the equality in the end, but such that this doesn't happen for any smaller beta. Okay, so we can return to some examples. We have already seen that if X is weakly sequentially complete, this is if and actually only if X is Baire order 0, because weak sequential completeness means that already the 0th element, the X, is sequentially closed. And we have already seen that the Banach space C01 has Baire order omega 1, because it never stabilizes in a countable step. Yeah, and finally, it follows from the theorem of Roder and Rosenthal that if we have a Banach space X that is not weakly sequentially complete and also does not contain L1, that it needs to have order precisely 1. This is because since it's not weakly sequentially complete, then by the first step we have that it cannot have order 0, and by the Rosenthal theorem, everything is a Baire1 functional, so it has to stabilize at most at the first step. Okay, so we see that we have Banach spaces that have order 1, 0, or omega 1. And it's interesting that so far there are no other examples of possible Baire orders of Banach spaces. So this inspired Argyros, Godfrey, and Rosenthal to actually ask whether this is even possible. Yeah, so this is the introduction to the problem, and the answer to the problem is yes, because we constructed a separable Banach space of Baire order 2. So in the rest of the talk, I would like to make a few comments about the construction. So the key building stone of our construction is the Azimi-Hagler space that was already mentioned today in a different talk. And in my opinion, it's a very interesting Banach space that doesn't get enough recognition, so I will try to advertise it a bit. So we have read that it's a L1 saturated Banach space without a sure property, and for us it will be important that it's not just without sure property, but that it is not even weakly sequentially complete. Yeah. So it's a Banach space that has a very nice basis. It's normalized by monotone spreading and boundedly complete. But for our purposes, it's important that the canonical basis of this space is non-trivial weakly Cauchy sequence. It means that it converges in the bidual to something that is not in X. And even more importantly, that this is essentially the only obstacle for weak sequential completeness. That this limit of the canonical basis is the only discontinuous Baire1 functional, essentially, in the sense that the continuous functionals are of codimension 1 in the Baire1 functionals. Yeah, so one can think about this Azimi-Hagler space as a kind of Baire1 variant of the James space. In the James space, you have only one new functional in the bidual, and here you have only one Baire1 functional in the bidual, even though you have many, many more functionals in the bidual. Yeah, so one of the important things why we consider this Azimi-Hagler space instead of the James space in the beginning was that this space is L1 saturated, so it doesn't violate the Odell-Rosenthal theorem. If we use the James space, it doesn't contain L1, so it would be hard to get something of Baire order 2. Yeah, but now it seems that we made some corrections and that our construction could actually work with the James space, but it's not checked, so for the Azimi-Hagler space it works. Okay, sorry. And here we have the norm. I'm not going to spend much time describing the details of the norm, but yeah, that this is the formula, and the important part of this definition is that this defines a basis that is very much not unconditional. And it's very important that it is not unconditional, because if we had some kind of unconditional variant of this, everything would be of Baire order 1. It can be shown that Banach spaces on conditional basis is weakly sequentially complete if and only if it doesn't contain C0. And if it does contain C0, we will still get only the first bare class. Yeah, okay, so the building stone for our construction is going to be the Arsene-Hagler space. And let me give you a few ideas of the construction itself. So the goal is to somehow build a separable Banach space X such that the complement of the continuous functions in the first bare class is going to end up being the Arsene-Hagler space. Because like motivationally, we know that the Arsene-Hagler space will give rise only to one new limit. So if the first increment is the Arsene-Hagler space, then the second increment should be 1 point, and then we will be done. So this, of course, needs more details, but this is the main idea. Because if we have this, then we could show that the second bare class is then just the first bare class plus 1 dimension. This is the new limit of the basis of the Arsene-Hagler space. And from this, it easily follows that the second bare class is already closed undertaking limit subsequences. So we would get these two, this equality and this inequality. And this is precisely what we want. This is what does it mean for the order to be 2. Yeah, so this is the key idea of the construction. And now let me draw a picture of actual details of the construction, not details, but more details of the construction. So as we heard in the morning, what is the nicest way to construct a separable Banach space? Take completion of C00. So this is exactly what we are going to do. And also for practical reasons, we are not going to take completion of C00 over n, but over this upper left triangle of n squared, which is a countable set, so it shouldn't matter. Yeah, so our x will be a completion of this C00 n squared and only of the elements supported in the upper left triangle. And we somehow need to define the norm in such a way that however we pick a column in this triangle, then we get something that is equivalent to the Arsene-Hagler space. So the columns of these triangles are Arsene-Hagler spaces. Yeah, so this will... Yeah, so this will give, by the properties of the Arsene-Hagler space, every column will give us one new element in the first bare class. So this is yeah, so for every column we get one more element. And to get to the first part of the key idea, we just need to prove 2 things. First, we need to show that these new elements here are the only new elements up to a norm closure of the first bare class. And further, we need to show that they are equivalent to the Arsene-Hagler spaces, Arsene-Hagler basis. Yeah, so the more complicated thing is the first thing, that we need to somehow show that going up through the column is the only possible way to get a new Berlan functional. And we do it by defining the norm in such a way that if we move, like in this triangle, not straight up, but diagonally in some way, then we get something equivalent to the little L1 basis. So you can somehow see the similarities to the combinatorial Banach space, where we had that if we go through chains, we get C0. If we go through anti-chains, we get L1. Here we have, if we go in one direction, we have Arsene-Hagler. If we go in multiple directions, 2, because there are only 2 directions, we get L1. So this condition will, in the end, essentially give us that if we have any sequence in X, then there are 2 possibilities. It's either essentially supported on finitely many columns, and then the possible weak star limits are only these finitely many points, or it is supported in infinitely many columns, but then we can extract L1 subsequence, and so it cannot be weakly Cauchy. So by this, we like artificially kill all the possibilities to converge diagonally. We only can converge when we go straight up in one direction. Yeah, so the second condition implies that this increment are the only new Berlan functionals. And finally, we also need to show that this new sequence is equivalent to the as in the hardware basis again, but this is easy just by choosing some specific norm. Okay, so yeah, so I guess that the key part of this construction, like this is, the first step is technical, but the key part is to get this point one, to get a specific increment in the first Baire class. And the technically key part, how we can do it, is this second point here, that we have a method how to kill diagonal convergences on the square. Yeah, and so this is it. And as I mentioned in the beginning, this is still a work in progress. So there is this more general, very natural question whether we can find for any given countable alpha a separable Banach space whose Baire order is precisely alpha, which is still open. We did it for alpha equals 2, and we are working now on the higher ordinals. It seems hopeful, but we don't have it proved down like the case for alpha equals 2, so I talked only about the case alpha equals 2. Yeah, okay, so thank you for your attention.